In 2022, generative AI tools became widely accessible, allowing a computer to synthesize text, audio, and high-definition video instantly in response to a plain English command. Because these systems respond to natural language, individuals with zero formal software engineering skills can now generate working software prototypes. You do not need to know how to write code to build a functional application. If a machine can write the code, what is left for the person who used to type it? The profession is currently shifting from manual syntax towards a practice called vibe coding. Vibe coding is the orchestration of foundation models. Rather than writing the exact instructions a computer must execute, a developer manages prompts, context windows, and interconnected AI tools to generate the desired result. Success in this environment requires a shift in perspective. To command these systems effectively, a developer has to understand the underlying architecture that determines how the model interprets a request. Traditional software used rigid decision trees, but generative AI uses probabilistic models. This stems from the 2017 transformer architecture, replacing older recurrent networks. Its self-attention mechanism processes data in parallel, simultaneously mapping the relational importance of each token. Processing all of those inputs in parallel improves the model's ability to grasp context, while making the training process far more computationally efficient. Specific architectural refinements, like layer normalization, stabilizes the data as it moves through the network. These improvements allow modern, sub-10 billion parameter models to routinely outperform older models that were 10 times their size. Grasping these internal mechanisms allows a developer to predict how a transformer interprets complex commands, turning a black box into a precise engineering tool. Orchestration now involves foundation models built on diverse data types, from images and patient records to complex biological omics. Feeding an AI varied datasets allows developers to synthesize bespoke molecular content. In pharmacology, generative models are actively mapping out novel configurations for drug discovery. This intelligence is also moving into the physical world. Physical AI connects generative logic directly to real-world hardware. Industries are currently deploying these systems in the form of collaborative robots on assembly lines, autonomous forklifts in logistics, and automated inspection drones. Prompting a standard web-based chatbot is simple. Deploying bespoke, multimodal AI to control heavy machinery or sensitive medical data requires a level of control and precision that simple prompt engineering cannot provide. Modern development requires integrating these complex data types into functional systems that operate reliably in the real world. We are already reaching the limits of unguided AI. Many companies are currently abandoning their generative AI pilot projects because of poor data quality and failed system integrations. Legal vulnerabilities are also mounting. Because these models require massive training datasets, major publishers and authors are pursuing copyright lawsuits against developers who use their work without permission. This government assessment identifies the specific risks inherent in these systems: unintentional bias, unsafe outputs, cybersecurity threats, a lack of data privacy, and the difficulty of assigning accountability when a system fails. Developers are responsible for solving these problems. They must design the human-in-the-loop oversight protocols that ensure an AI does not generate malicious software or compromise sensitive personal data. Developers integrate systemic guardrails directly into the architecture of every application they build, treating risk management as a core technical requirement. This graphic illustrates the physical cost of generative AI. Within the cube, glowing server racks sit alongside a factory emitting smoke, representing the environmental footprint of the data centers powering these models. These facilities drive up electricity demand, consume millions of gallons of fresh water for cooling, and generate mounting electronic waste. As governments introduce new environmental regulations, the task of building efficient, compliant models falls heavily on the technical architects. Modern developers serve as the bridge between the scale of generative logic and the safety of the physical world. The machine can write the code, but mastering generative AI requires the foresight to orchestrate that machine safely, efficiently, and responsibly.